So this is going to be a talk about foundations of probability theory. It's a talk about predictive inference. It's a talk about exchangeability. The one word you might not be familiar with is the word imprecise. Yes. So it is going to be about probability, but not the way you're used to it, I think. And it's not the way you're used to it because it is imprecise probability. So in a sense, what we're trying to do in imprecise probability is use the same foundations as, for instance, Finetti was using the coherentist, rationalist, operationalist foundations that Finetti was using, but trying to make or to take imprecision and indecision seriously. That's what we try to do. So let me go very briefly and start with the most basic model. Let's use this simple graph here. What I've drawn here is a probability simplex. It's an experiment with 3 possible outcomes A, B, C, but it translates easily to a finite number of possible outcomes, any finite number. And I've drawn the simplex of all the probability mass functions, which in this case is this triangle. So any point in this simplex is a probability mass function. Yeah. Now what is the easiest way to think about an imprecise probability model is to look at it as a convex closed set of precise probability models, a convex closed set of mass functions, like the blue thing you see here. It's a convex closed set of, and this is an imprecise probability model as we use it. Now, if we have such a model, we could ask, what is the probability of C? Well, in that case, any model in this is a candidate model, any point in this is a candidate model, and the probability of C is just the distance to this line, and it ranges between 1/4 and 4/7. So what we say is that we have a lower possible value, which is 1/4, and an upper possible value, which is 4/7. And that is what we say. We have a lower probability and an upper probability for C. We can do this for C, but we can do this for any function on the set of possible values, A, B, C. So in general, if we have a set of possible values, script x, then we can look at any real valued map, f, on that, any map from x to r, and for any candidate model, any point in this blue set, we can calculate the prevision or the expectation associated with that mass function. So any point is a mass function, calculate the expectation under that mass function, that gives you a real number, and then allow all the mass functions to range over this blue area. This blue area we call a creedal set. And if we do that, then this ranges over an interval, and the lowest value for that interval we call the lower expectation, or the lower prevision of that function, and the upper value is then the upper prevision or the upper expectation for this function. So that's the basic idea. If we have a creedal set, we can also associate with that two functionals that map functions into real numbers, a lower and an upper expectation. I say 2, but actually 1 is enough, because there is this general relationship between the two. If I know the lower expectation for all the functions, then I can calculate the upper expectation using this condition, which is called the conjugacy equation. It says that the upper expectation of minus a function is minus the lower expectation of the function. So we will concentrate on lower expectations. What we do here, we started with a set of mass functions, but you can also go the other way around. We can define a lower expectation or a lower prevision by itself. We will call a functional on all the functions on x. So this is a map that maps a function to real numbers. We will call that a lower prevision or a coherent lower prevision if it satisfies the following 3 properties. This is the boundedness properties. It says that the lower expectation should always be higher than the minimum of the function. This one says that the lower expectation should be super additive. The lower expectation of a sum of 2 functions should always dominate the sum of the lower expectations. And this one is the non-negative homogeneity condition. It says that if I have a non-negative constant inside, I can take it out, but only non-negative constants. So these 3 properties define what we call a coherent lower prevision. And then there's a very simple theorem that says that any coherent lower prevision, or a functional is a coherent lower prevision, if and only if there is a creedal set in this sense that generates it in this sense. So it's a one-to-one relationship. We can either start with creedal sets, or we can start with these lower and upper expectation operators. It doesn't matter which we do. So much of the theory of in the early theory in imprecise probabilities of Creedle sets and lower and upper provisions, dealt with just that, Creedle sets, lower and upper provisions, but it's a bit complicated. Mathematically, it's a bit complicated doing that. And in order to explain why it's complicated, let's look at the more interesting case of two variables. We have now two variables. A variable in a space x of 1 and another variable in another space x of 2. If we want to model the joint information, what we will do is now, we will not look at the functions defined on x1 or x2. We look at the functions that are defined on the product of x1 and x2. And then this functional will now be a lower expectation that maps functions on the product space to real numbers. That is our basic model. And a conditional lower provision, well, we fix one of the variables, and then we say, for the functions of the other variable, we just say, okay, we have for this variable conditional on the fact that the first variable assumes the value is 1. We have a lower provision operator for functions of the second variable. And that we call a conditional lower provision. And then we can have coherence criteria that tell us how a conditional and a joint model, how these should be, how they should combine with each other, how they should cohere with each other. And these criteria are coherence criteria. They're very similar to Bayes' rule. They're very similar to, actually, to De Finetti's coherence criteria for the precise models. Okay, there's one complication that I want to mention now, that is that if I have a joint lower provision, then it will not always uniquely determine a conditional. This is similar to what happens in what we call precise probability because of problems with probability 0. Right? So that is a problem, that's a complication. But let's now move to the more general case, because when I do predictive inference, we will need to talk about many variables. So let's introduce some simple notation. I will look at a number of variables, and I index them by set n. And so I have a number of variables that assume, so a variable x of I that assumes values in a script x of I. Okay. And then, to simplify the notation, if I take a subset of the index set, then I can collect all the corresponding variables into a tuple, and I will denote that tuple by x sub s. So x sub s is a tuple of variables. Yeah. It's a collection of variables together. And it assumes values in the product space, yeah, which I will also denote by script s sub s, just to so when you see a capital here, it means that I have a tuple of variables, a collection of variables taken together. That's all that we need for notation. Another thing that we will need is, to define a lower provision, I will need an input and an output pair. So I take two sets of variables, an input set and an output set. I'm going to condition on the input set. So I'm going to assume that I know that the input variables assume a certain value, and then I'm going to say what is then the lower expectation of any function of the output variables. Conditional on the fact that the input variables assume a certain value. So this is my notation for a conditional lower provision. And then, just to show you how complicated things can get, this is a coherence criterion. If I have a number of conditional lower provisions, they have to cohere, they have to satisfy rationality criteria, very much the same way as Bayes' rule and De Finetti's coherence criteria. Well, this is a typical example of coherence criterion. In precise probability theory and standard Bayesian theory, this single term here will be replaced by another sum. Yeah? So the fact that we're imprecise makes sure that this is easier in a sense. It's a bit less complicated. Yeah. But if you look at these formulas, it's really horrible. And the fact that it's really horrible, cumbersome, and complicated is what I think is responsible for the fact that imprecise probabilities are not very popular at this point, mainly because they're mathematically very complicated to work with. It's complicated, it's cumbersome. There are a few papers, amongst a few that I did, that try to brave these complications. One of them is dealing with the law of iterated expectations and the coherence of that law or the law of total probability, if you want, in imprecise probabilities. Another one is weak and strong laws of large numbers. All these papers try to deal with coherence in this traditional way, and if you look at the proofs, they are absolutely horrible. It's not fun to read them, and it's not fun to write them either. There is, I think, one way out of this, one very promising way out of this, and that is using another type of model that is in fact, conceptually came before the lower and upper provision approach and the set of probability approach, which is the set of desirable gambles approach. And what I'm going to do now is try to explain how this works. Now, why would we want to do it? Well, there are a number of advantages. I've written down a few here. It's simpler, it's mathematically simpler, it's mathematically more elegant to do this. It gives you a language that is more expressive, that can say more than using provisions and sets of probabilities. It is a geometrical language. It has a geometrical flavor, so if you are geometrically inclined, it's easier for you to work with, I think. It shows, and this is nice, I think, it shows that much of what is probabilistic inference, that, for instance, Bayes' rule, that they are special cases of what you could call logical inference, or formal logical inference. It has, on the one hand, propositional logic as a special case, and precise probability as a special case. So it encompasses both approaches into one language. And another thing is, and this is very nice, and that is why I'm also going to talk about it here, it avoids problems with conditioning on sets of probabilities. There are no problems with probability zero and conditioning there. So what is this approach? Well, it's not new. It's, I think, the first real paper on this was written by Williams. He wrote it down in '77. It was only published 30 years later. So it was a set of notes that were widely circulated at the time in '77, Peter Williams. And then Peter Wally used it in a paper towards the unified theorem of precise probability to develop it further. But since then, a lot of work has been done in this area. Let me try to explain how it works. We'll use the notion of a gamble. A gamble is just as we had before. It's a function from the set. So we have an experiment, a random variable. It assumes values in a finite set X. I've looked at the case heads and tails here, but you can do it in any finite dimension. And a gamble is just a function from X to the real numbers. So in this case, it's just two values, the value in heads and the value in tails. So it's a point in two-dimensional space. And so a gamble is a point in a finite dimensional space. And it says that, and a gamble is an uncertain transaction. It will give you, if it's heads, it will give you -1 reward, and if it's tails, it gives you 1.5 reward. So it's like an uncertain transaction, and then the idea is that we're going to model a subject's uncertainty by looking at the gambles that he accepts. So we ask a subject, give me a number of gambles that you accept. And this is going to be your uncertainty model. So your uncertainty model is no longer going to be a provision or an expectation or a probability. It's going to be a set of gambles that you accept, or, in fact, more than accept, you strictly prefer them to zero. So it's better than zero. Zero is the status quo, nothing happens. If you think this gamble is better than zero, you will say that this gamble is desirable to you. And what we're going to do is collect these gambles in a set D, and that is, the set D is now going to be your basic model. That is the model that you're going to use. We're going to forget about probability measures, we're going to forget about expectations, we're going to use sets of desirable gambles as our probability models. Not any set is a good set, of course. We're going to impose rationality and criteria. The first one is a sort of avoiding sure loss condition or avoiding partial loss condition. It says that if our gamble is either zero or negative, then you're not going to think it's desirable. It's like avoiding a Dutch book. Very simple. The second one is if your gamble is everywhere non-negative and actually positive in some points, then you're going to accept it, because you can't lose. Why reject it? Why not accept it? You can't lose from the gamble, so accept it. And then the third is actually that it says that you're working with linear utilities. It says that if I have two desirable gambles, and I take the combination of the two gambles, then that should be desirable as well. And if I have a gamble and I multiply it with a positive number, I apply a scale to it, then it should still be desirable, the result. Yeah? So this is really working with linear utility, and this is just avoiding sure loss and accepting a partial gain. Very simple axioms. Okay, what does this mean for our set of gambles that we find desirable? Well, it says that the first orthant should be acceptable, should be green. The negative orthant should be forbidden, is red, because nothing in here should be accepted. And then the third and the fourth axiom just tell us that, if you look at it, They tell us that a set of desirable gambles is a convex cone. Right? So it's closed under positive linear combinations. So this is the set of desirable gambles. It's a convex cone that includes the first orthant and excludes, has nothing in common with the negative orthant. Yeah. So anything like that is a set of desirable gambles. So what is the relation with precise probability models now? If I increase my set of desirable gambles, now let me look, does it look a bit like this? Yeah? If I increase it, what happens is I get larger and larger and larger, and until at some point I end up with a plane, right? I end up with a plane. Can I go further than a plane? Or a semi-plane? Can I go further? No, I can't, because if I went further, the sum, let me just do this, if I had a gamble here and I had a gamble here, the sum of them would end up here. And that's the forbidden area. So I can never go further than a semi-plane. So the largest possible sets of desirable gambles that are coherent are these semi-planes. Now a semi-plane is completely characterized by its normal, right? And the normal is a probability mass function. Okay? It just says, so a semi-plane is actually a precise probability model. It says, okay, the expectation, if the expectation is positive, I'm going to accept it. If the expectation is negative, I'm going to reject it. So that's a precise probability model. There are other precise probability models, there's an infinity of them. So the semi-planes ones are the precise ones, the imprecise ones are the cones. Yeah? And the smallest one, the most conservative one, is of course the green one there. This green model is the smallest possible coherent set of desirable gambles. So from now on we're working with these models and not just semi-planes. We're working with cones in general. That's the idea. Okay. Now, there's a connection with the lower provision, the model that we used before. The idea is take any gamble. So this is a gamble and you get it. This is why it's positive. And you give away a constant number alpha. So you're paying a constant amount of alpha in order to get the uncertain f. So you're buying the gamble f for a fixed price alpha, and the result of that transaction is desirable. Yeah. So you're willing to buy f for alpha, and the highest price for which you're willing to do that is your supremum buying price, is your lower provision. So this gives you a behavioral interpretation to a lower provision. It's a supremum buying price. You can do the same for an upper provision or an upper expectation operator, but this means that if I have a set of desirable gambles, I can always derive a lower expectation operator from that, in this sense. Okay? Graphically, I start with a function f, I subtract an alpha is a constant thing, which means that it's parallel to the first diagonal. I go until I hit the border, and when I hit the border, this distance is a lower provision. Okay? This already tells you why a set of desirable gambles is more informative than a lower provision. Because in this set of desirable gambles, the border could be included or it could be excluded. But this will not affect the lower provision, because whether the border is included or not, the supremum is going to be the same. It will not affect my lower provision. And it's this border behavior which is allowed in sets of desirable gambles, but not taken into account in lower provisions, which makes sure that there is no problem with conditioning on sets of probability zero. Because conditioning on sets of probability zero is precisely problematic on the border. Okay. How do we do inference with these models? How do we do probabilistic inference? Well, it's very simple. Because if you go back to just to these axioms, these are logical axioms, right? They are formal logical axioms. They are production axioms that you can use to make inferences, just like you do in classical propositional logic. So the idea is very simple. Assume that I have a subject who tells me, okay, I have a number of gambles that are acceptable, desirable to me. This one, and this one. These are desirable. What is the smallest, the most conservative model that corresponds to this? Well, it must include all the positive ones, right? So this must be there, and it must be a convex cone. So take the smallest convex cone, and that's it. This is our model. This is what we call the natural extension. It's the smallest model that includes all the assessments and also all the positive gambles. And this is probabilistic inference in a nutshell. Everything, or most of what we do in probabilistic inference, is a special case of this very simple argument. The posy here is just taking all the positive linear combinations, so it's the smallest index term. All right. Now, there's more to inference, of course, because when we have more than one variable, what we want to do is we want to marginalize, we want to condition. How do we do this in this language? How do we marginalize, how do we condition? Now, marginalizing is very easy. I have a number of variables. I have n variables, and they are just a tuple of variables in this product set x of n. Now take any subset of variables, and we want to find the marginal. So our model is just a coherent set of gambles. Gambles on what? On all the variables together. So I just take gambles, functions, real valued functions, and all these variables together. And a number of them will be desirable, and they are collected in this set of desirable gambles. And now we want the marginal, the gambles that only deal with the I variables. So I take a subset of variables. How do I find the marginal? Well, in my set of desirable gambles, I just pick out the ones that only depend on the I variables. Not that don't depend on the other ones. If I take that, this is what I do, I take the intersection with the gambles that only depend on the I variables. If I do that, I have a margin. Just taking out the ones, marginalization is very simple. How do we condition? Well, conditioning is also quite interesting and nice. Suppose I have an observation, I have an input set, and I say, okay, the I variables are equal to a given value x of I. How do I condition my set of desirable gambles d on this information? So how do I get to a new set of desirable gambles, which is now a set on the remaining variables? So it's on n minus I. How do I do that? Well, this gamble is desirable in the updated set. This is my symbol for the updated set. If and only if the product of this gamble with the indicator of the observation is desirable in my original model. Now what is this gamble here? This is a gamble, and it's a called off gamble. It means that this gamble here is 0 unless this event occurs. So the gamble is called off unless the conditioning event occurs, and if the conditioning event occurs, this is 1, and I get the gamble G. So the idea is, my gamble is desirable conditional on the observation only if the called off gamble is desirable in my original model. This is updating. It has Bayes rule as a special case. Yeah? So Bayes rule follows from this simple formula. Interestingly, I see no problem. This always works. As soon as I have a set of desirable gambles, I can, for any I, any observation, I can go to an updated gamble. There is no problem with conditioning on sets of probability 0. It always works. I always have a unique updated model. No problem with conditioning on sets of probability 0. So now I can use this idea to produce conditional lower provisions. What can I do? For instance, I take an in-conditioning variable and an input and an output variable, and I say, okay, I have a conditional lower provision, conditional on the observation x of I, and I take a gamble on the O variables. What is the conditional provision for G given xi? So what do? I use the formula that I had before, this formula, but instead of using the set of desirable gambles D, I'm now going to use the conditional set of desirable gambles. This one. I'm just going to use the updated set of desirable gambles. Or in terms of the call of gambles and the original set of gambles, this is this formula. So I have a way of, if I have a set of desirable gambles, I can produce any number of conditional lower provisions under any type of observations. And the interesting thing is that the coherence criteria now become very easy. Because suppose that I have a number of conditional lower provisions. So I have input and output variables, I have a number of conditional lower provisions. When are they coherent? Remember the very complicated formulas that we had before? Well, now this becomes very easy. When are they coherent? If and only if there is a set of desirable gambles, a joint set of desirable gambles that produces them. So the coherence formulas and conditions that we had before now is just find a set of desirable gambles, a joint set of desirable gambles that produces precisely these conditional lower provisions, and they will be coherent. So this becomes much easier now. And working and so instead of working with lower provisions, we're going to work with sets of desirable gambles because the mathematics is much, much easier. There's a few papers that work with sets of desirable gambles that avoid all these complications. One paper is where we show that this idea of desirable gambles is very closely related to Schaefer and Vocht's game theoretic probability approach. There's a very strong formal resemblance between the two things. Another one is it deals with independence independence notions in imprecise probability theory. The next thing I have to do is talk to you about exchangeability. So now we have these sets of desirable gambles approach. I'm assuming you're familiar with this now, more or less. You know what it means. Now, how can we deal with exchangeability in this approach? Well, exchangeability is a type of symmetry. And symmetry, let's assume that we have a variable x, it's assumed values in a finite set, and there is a symmetry group, a permutation group associated with that space. And we're going to assume that the symmetry is expressed by this symmetry group, by the group of permutations. So, and this is permutations of the space x, of the possible values of my variable. What I'm going to do is I'm going to lift these permutations from the set x to the set of all the gambles on x. So take any gamble, a function f on x. I'm going to lift it, and I call this the permuted gamble. It's just a composition of f and pi. So the idea is that the value of the permuted gamble in x is the value of the original gamble in the permuted value of x. So this is lifting this permutation, and once we do that, we know that this is actually now a linear transformation of this vector space. The set of all the gambles is a vector space. It's an n-dimensional space. And this is just a linear transformation, actually a linear permutation of this thing. And so now I have a group of linear permutations of this space of gambles. And I'm going to express my symmetry using that. How am I going to express that a subject thinks that there is symmetry? If I think as a subject that there is symmetry, it means that I will be indifferent, in a sense, between a gamble and its permutation. I will not distinguish between a gamble and its permutation. Or in other words, if I have a gamble and I subtract the permuted gamble from that, the result is going to be equivalent to 0 for me. It's not going to matter. Yeah? Expressing this is actually a behavioral way of expressing indifference. It's just that I make no difference between a gamble and its permuted version. And so what I get from this is a number of gambles that are, to me, equivalent to 0. So I have any gamble, its permuted version, I've subtracted, it's equivalent to 0. So I get, and I take the linear span of all these things. This is a linear space of gambles that are indifferent to me. I don't care. To me, they are 0, in a sense. Okay, so I have a linear space of indifferent gambles. The question now is, on the one hand, I have this indifferent gambles. On the other hand, I have my desirable gambles. How do indifferent and desirable gambles work together? Well, actually, you can show that a very nice way in which they can work together is if they satisfy this condition. It says that if I have a desirable gamble and I add an indifferent gamble, then the result should still be desirable. That's the idea. So indifference does not affect my desirability. It's a very simple idea. If something is desirable and I add something that I don't care about, that is equivalent to 0 for me, then the result should still be desirable. That is the formula that connects the two together. Okay? Now, what happens, what is a consequence of this, and this is, I think, is quite nice. Let's now look at the space of all what we call the permutation invariant gambles. So take any permutation. If a gamble is equal to its permuted version, then and this for all the permutations, then I will call this gamble a permutation invariant gamble. It doesn't change when I permute it. Yeah. And I'm going to use, this is also a linear space. So I started with my linear space of gambles, and now I have a subspace of all the permutation invariant gambles. Well, there is a projection operator, an operator that projects any gamble to its permutation invariant equivalent in the following way. What I do is, I will take a gamble, f, I will take all its permutations, and then I will take the uniform average of them. Yeah? This gives me a new gamble. And the nice thing is, so this gives me a way to turn a gamble, a vector, into a new vector. So I have a transformation, and it has the following properties. It says that it doesn't distinguish between a gamble and its permutation. Also, the result of this operation is permutation invariant. Another thing is it's a projection operator. If I take it twice, it's the same as doing it once. So that's a definition of a projection operator, yeah? Also, the range where I get to is exactly the space of all the permutation invariant gambles. And what is really interesting is that the kernel, the things that are mapped to 0, the kernel is actually my set of indifferent, my linear space of indifferent gambles, which is really nice. Now, this is basic linear algebra. If I now use the dimension theorem that says that any gamble can be uniquely decomposed in this way into f minus the projection of f plus the projection of f. This is an element, this is permutation invariant. And actually this is an element of the invariant, of the indifferent gambles. These are equivalent to 0. This is very easy. But using this very simple result, you have what I call the symmetry representation theorem that says that if I have a strongly invariant set of desirable gambles, in other words, one that is satisfied the symmetry, then a gamble is desirable if and only if its projection is desirable. It's very simple consequence of this. But what this means is that in order to check whether a gamble is desirable, I only need to look at the projections, at the invariant gambles. Yeah? So I have a much lower dimensional representation. What you're seeing here is De Finetti's representation theorem for exchangeable gambles in a very elegant algebraic form. Yeah? This is De Finetti representation, nothing else. Yeah? But in terms of sets of desirable gambles. Okay. A little bit more detail, because I need to get to a little bit of mathematics before we can actually get to the results that I describe in the paper. I have these permutations. I have a category X, a possible observation. I can apply all the permutations to it, so I will jump around in my category space, and I get a set. And this set I denote by this square angle or square parenthesis X. And this is what we call an invariant atom. It's the smallest invariant set. And these atoms constitute a partition of the original category space. Yeah? These are the smallest permutation invariant sets. Yeah? And actually, a gamble that is permutation invariant is a gamble that is constant on these partitions. Yeah? So what happens with this representation is that instead of looking at gambles on the original space, you're now looking at gambles on the atoms of this space. So which is why there is this huge reduction generally in dimensionality of the problem. This is why exchangeability simplifies things a lot. Okay, now we get to exchangeability, because this was in general about symmetry. This was not about exchangeability in particular. It's a general symmetry result. For exchangeability, what we're going to do, exchangeability means that I have a number of variables, x1 through xn, and I'm expressing that the order in which I observe these variables doesn't matter. So I'm going to have permutations on the index set, the time index, and there will be permutations on these. So take any sequence of observations, I can permute them just by permuting the indices, and this gives me a permuted x. So this is the permutation that I was talking about in the previous slide, this pi. It's just you have a vector of observations and you permute the indices, and this is your permutation of the space. Interestingly, the permutation invariant atoms can be completely characterized by what we call the counts. Let me give an example. Suppose I have a space, two possible categories, A and B, and this is the set of observations, AA, BB, A, BB, AA, and so on. Yeah? If I permute the time indices, there is something that remains equal, that remains the same, and that is the counts. The number of times I have A and the number of times I have B. The number of times I have A, I will call T sub A of X. And this is part of this general definition is that if I have a category Z, then T sub Z of X is, what I do is in the sequence X, I just count the number of times that I have category Z. And so this is the count vector. So in this case, for this sequence of observations, my count vector is 6 times A and 7 times B. And that is the thing that doesn't change by permuting. Right? And actually, it turns out that if I look at the permutation invariant atoms, they can be completely characterized by their count vector. It's just it's just the sequences that have a given count vector. Yeah? So counting becomes important. How many are there? Well, so many. The multinomial coefficient. Right? That's how many elements there are in that atom. Interestingly, now this becomes really nice, I think. What I can do is, I have an atom, a number of observations that I can get from each other by permutation, yeah, by all the permutations here, I have this atom. I can look at the uniform distribution on this atom. So I look at the expectation operator that is associated with a uniform distribution. So I give the same mass, this mass, to all the elements in that atom. Well, this is an expectation operator, and it's the expectation operator for the hypergeometric distribution. Yeah? It's sampling from an urn with composition M. Yeah? So there are as many balls, types of balls, as there are categories, and the count factor M determines how many balls of each type there are. And this hypergeometric expectation operator is just the one that describes sampling from an urn. Yeah? And interestingly, the projection operator that I was talking about is precisely this hypergeometric expectation operator, which is why hypergeometric expectation and sampling from an urn is so closely connected to exchangeability in the finite case. What happens in the countable case, which is the real Definetti representation theorem? Well, I will give you a version of the representation theorem, of Definetti's infinite representation theorem, that you're probably not familiar with, but it's, I think, one of the most elegant ones. It will take me some time to explain it. I have a number of random variables, right? A number of variables, x1 through xn, in a finite category set. Then it's exchangeable if and only if there is a unique coherent expectation operator or coherent prevision on the linear space of all the polynomials on sigma x, and this is just the simplex of the mass functions. So sigma x is the mass functions, the set of all the mass functions on x. Yeah? And what I'm doing is I'm taking polynomials. These are multivariate polynomials. Let me explain. This one here, let's look at this one. This Bm of theta. Theta is an element of the simplex. It's a mass function. Yeah? There are as many components as there are elements in x. So it's an element of this simplex. And what I'm doing is I'm looking at this. So what I'm doing is theta to the number of times I see x multiplied with this multinomial coefficients. It's a multinomial mass function, right? It's the mass, it's the probability of observing a sequence m, a count vector m. But if you look at this as a function of theta, it's a multinomial. Yeah? It has a name. It's called the Bernstein basis polynomial. Yeah? And it's called a basis polynomial because if I vary the m for a constant n, for a constant number of observations, it constitutes a basis of all the polynomials of degree n, up to n. Yeah, so these are basis polynomials. So what I'm doing here is taking a linear combination of these basis polynomials, so I'm having a general polynomial, and the coefficients are just the hypergeometric ones. Actually, this thing here, the thing that you see here, is actually the multinomial expectation operator. You can see that that's a detail. So this, what I get here now, and now what we see is that this is a polynomial on the simplex, and if I take any function of the first n variables, its expectation will be given by the prevision, the h, the representation of this polynomial. This is Definetti's representation theorem, but in terms of polynomials. So the idea is I can represent everything as a expectation operator on the polynomials on the simplex, which is a huge dimensional reduction. This brings us to, this was with previsions, this is precise probability theory. Now we come back to imprecise probability theory, sets of desirable gambles. We have a model, a number of random variables. We have a set of desirable gambles for the first variable, for the second, for the first two, for the first three, for the first four, for the first n, and so on. These are all sets of desirable gambles. They are coherent. When are they exchangeable? Well, this is our representation theorem. It's very similar to Definetti's representation theorem. The only thing is that the expectation operator on the polynomial is replaced by a set of polynomials. Yeah? So it says that a gamble is desirable. A gamble of the first n variables is desirable, belongs to my set of desirable gambles, if and only if the multinomial expectation of f, so this is this function here, but this is a function of theta. So as a function of theta, this is a polynomial. Well, if and only if this polynomial here, as a function of theta, belongs to what we call the representation, so the set of polynomials here. And this H has certain properties. It's Bernstein coherent. In a sense, it's coherent. It's a cone. It's closed under addition and positive multiplication, and it does not contain negative polynomials, and it contains all the positive polynomials. So this is representation. But there's something more. One thing more. Suppose that we now have observed, and this brings me to predictive inference. Suppose that we have observed a number of variables already. I have observations for the first n variables. I have a vector containing observations for the first n variables. Then, as a consequence of our definition of exchangeability, it follows immediately that the remaining sequence of variables is still exchangeable. Yeah? So exchangeability is preserved under observations. Not with probability 1, because there's no problem of conditioning on probability 0. It will always be still exchangeable. This is because we work with sets of desirable gammas and not with expectations or probabilities. So it will be still exchangeable. If it's exchangeable, it's an exchangeable sequence. It has a representation. It has a set H. And I will call this set H conditional on X. This is the representation. This is a set of polynomials that represents this model. First of all, you can prove that if I take any permutation of X here, if I permute the indices, the model is not affected. The representation is not affected. So it only depends on the count factor. So the count factor is a sufficient statistic for inferences under exchangeability. We know that in the precise case, it also works in the imprecise case. The count factor is a sufficient statistic. And actually, we can obtain this representation very easily from the original set, from the original representation, using this formula. A polynomial belongs to the updated set, to the updated representation, if and only if the product of this polynomial and the Bernstein basis polynomial that corresponds with my observation X, with the count factor of my observation, is in the original set. Yeah? So if I know H, I can find all the updated representations. For any observation that I can do, if I know H, I know all the updated models. Immediately. They follow immediately. Yeah? So giving an H characterizes, and this is important, characterizes all the inferences, all the predictive inferences that I may want to do. Just give me a set of polynomials and it characterizes everything. Yeah? Which I think is quite nice. So this set of polynomials is in a sense the equivalent of a prior density on the simplex of all the mass functions. With the additional advantage that with prior densities you have sets of probability 0, there may be problems of conditioning on sets of probability 0. There is no such problem here. Yeah? There is no problem with conditioning on sets of probability 0. Okay, this brings me to my last slides on predictive inference. This is what our paper is about. But I needed all of this to explain to you what imprecise probabilities can do and how it can be useful. So let's now look at what predictive inference systems can do. Remember what I said is, if I have a set of polynomials on the simplex associated with a category set, that characterizes all my inferences about that variable, all my predictive inferences. So what I'm going to do is I'm going to define a map. So assume that we have a map that associates with any category set a set of polynomials. So that if you give me a category set, I know what the set of polynomials is, and all the inferences are completely fixed, completely characterized. I will call that map, I will call that a predictive inference system, because it fixes for all the possible category sets, it fixes all the possible inferences. Yeah? Finding such a map would be the program of logical probability theory, right? This is the aim of Carnap. Carnap, what he wanted to do was find such a map. Yeah? I don't like that idea. I'm too much of a personalist to like that idea. But there is something to it. Yeah? Because if we define such maps, then what we could do is we could use inference principles, like things that you find reasonable, to constrain these maps, to show that, okay, I want to impose this inference principle or this inference principle, what is still possible now? And you can study inference principles if you introduce maps like this. Yeah? Of course, taken to the extreme, if you impose many principles, you will reduce the number of possible maps to almost nothing, and then you have Carnap's program. Or if you want also Wally's program with his IDM family. just to give you a few examples of what could be interesting reasoning or inference principles. The first one, renaming invariance. Renaming invariance says that the names that I give to the categories should not matter. If I call category A ape, or if I call category A apple, that should not influence my inference. So I think that's a fairly reasonable assumption to make. If any inference system that does not satisfy this would probably not be a very good one. There's another one that is more controversial. I think it's a pooling invariance principle. It says that if I want to make an inference about a gamble that does not differentiate between two categories, it gives in two categories the same value, then I should get the same inferences if I use my original set of categories, or if I use a new set of categories where those two categories where my gamble does not differentiate are pooled together into one. Yeah? So if I pool, that should not matter for gambles that do not differentiate between the pooled categories. That is the pooling invariance principle. It's a bit more controversial, but well, to me it sounds reasonable. There's another one, specificity. Specificity is an interesting one. It's used very often in Bayesian inference, I think. It says that suppose we're observing something, we're trying to make predictive inference about something, and after a while we decide that we're no longer interested in categories that fall outside a given category Y. So we have an original set of categories X, and we take a subset and we say from now on we're only interested in this Y categories. I'm no longer going to look at the non-smokers. I'm only going to concentrate on the smokers now, for instance, something like that. Well, specificity says that from the previous observations, if I do this, from the previous observations, I can now eliminate all the non-smokers. Yeah? In my counts, I just eliminate all the non-smokers. If my system is specific, then this will be allowed. This is what happens. Interestingly, there is no precise inference system that satisfies all these principles together. No precise probabilistic inference system that does this. We know, since the paper, we know an infinity of imprecise ones, but there is no precise one that does all that. But another thing maybe is that as a consequence of this, of these three, well actually as a consequence of the first two, what we have is that if you take any observation, any sequence of observations, its lower probability, its prior lower probability will be 0. So we immediately get to problems, if we want to do inferences, we get to problems of conditioning on sets with probability 0, because the prior probability is always going to be 0. So this is why, if we want to deal with this type of thing, we cannot use, or it's very difficult to use lower provisions or sets of probabilities, and we have to use sets of desirable gambles, because that's much easier. And if we do that, there's a way, what we did was we just formulated all these three principles into the language of sets of desirable gambles. Now, I don't expect you to read this, just look at it. Yeah? Look at the form. They're basically the same. They're formally very, very similar. Yeah? And so that's what, at some point, tipped us over and said, okay, let's try and investigate this problem. It's a difficult mathematical problem, but let's try and investigate it. And so we showed that there's an infinity of systems that satisfy these three properties. And that's part of that is in the paper. It took us the better part of a year to get. Let me give a few examples of systems that are specific, that are pooling invariant and renaming invariant. What we're going to use is Dirichlet's on the simplex. Yeah? So this is the simplex, and we're going to use Dirichlet priors. And the parameters are just the Dirichlet parameters alpha, the Dirichlet strengths. And I'm going to look at a set of Dirichlet strengths, Dirichlet parameters. So there are as many real numbers, strictly positive real numbers, as there are components in X. And I'm going to look at all the ones for which the sum, the total strength, is smaller than some positive number S. This is my delta set. So it's Dirichlet parameters such that the total strength is smaller than S. Now define a set of polynomials for this given S. All the polynomials for which the Dirichlet expectation for alpha in that set is always strictly positive. Yeah? So I take all the Dirichlet polynomials for which the Dirichlet is strictly positive, the expectation is strictly positive. This is a cone of polynomials, and you can show that this produces an inference system that is pooling invariant, renaming invariant, and specific. Yeah? It's a very specific example of them. Actually, you can give the lower and the upper probabilities here. If I observe a count vector m, then the probability of observing an x immediately afterwards is this. Is just the number of times I've seen x divided by the total number of observations plus this s here, the total strength. And the upper probability is just the number of times I've seen x plus s divided by the total of number of observations plus s. So these are the lower and upper probabilities. There's one more I want to show you, which is this one. Take the union of all the Dirichlet ones, so these ones, the Dirichlet ones, these are for a given s. Now take the union of all these sets of polynomials for all positive s. So put them, you get a huge set of polynomials. Yeah? And a large set of polynomials means a very precise model. It means that I'm getting close to this semi-plane. Right? Well, actually, you can show that the posteriors for this model are precise. They are the Haldane posteriors for this model. What you do is you just use the observed frequency as your real frequency. These are the Haldane model. This model is pooling and renaming invariant and is specific. So the Haldane posteriors satisfy this property. Now what is interesting is that usually the Haldane posteriors are derived using an improper prior, the Haldane prior. Yeah? But this is not necessary because this is a coherent system. It means, actually, if you now go back, it means that there is an infinity of precise proper priors that produce the Haldane priors also. Yeah? So you don't need this improper prior. There is an infinity of precise proper priors that produces the same posterior. This is a consequence of the mathematics that we do as an immediate. This was proved in another way by Peter Wally in 91, but our argument is completely different and similar. So there's nothing wrong about the Haldane posteriors. They are perfectly sane in that respect. That's why I want to stop the presentation. Thank you very much.